Hey, if you are new here, this is Chandan and you are watching the Learning Field. This is the lecture 7 of our LPP. Okay, so this is the lecture series of LPP which we are continuing in this lecture series, the linear programming problem, and this is helpful for GATE exam, CSIR NET exam, and any state level set examination and many different other exams in which LPP are included in the syllabus. Okay, so we in the last lecture or in the last session we completed or we discussed the BGAME method. Okay, BGAME method which is in simplex method, and in this lecture we discuss the two-phase simplex method. Okay, so first in the second last lecture we discussed simply simplex method, then we discussed BGAME method, and then in this lecture we will discuss here two-phase method. Okay, these three are the methods of simplex methods. Okay, so before starting I am requesting you to all those who are new in my channel, those who are not watching me previously, please like, comment and share and subscribe the channel. Okay, and one more thing is that the PDFs of these classes will be shared in the Telegram channel of the Learning Field. So the Telegram channel link will be in the description and also here जो चैनल यूट्यूब का अबाउट सेक्शन में आप लोगों को मिल जाएगा. ठीक है, तो वहाँ से आप लोग टेलीग्राम चैनल को ज्वाइन कर सकते हो फॉर पीडीएफ्स एंड एनी अदर योर फॉर फ्यूचर रेफरेंस. ओके, सो लेट्स स्टार्ट. एंड दोज हु आर नॉट वाचिंग दिस सीरीज, okay, this series is very helpful I think, and we will cover the syllabus such a way that this series is helpful for GATE exam, SET exam, any state level SET exam, and also for CSIR NET exam. Okay, so let's start. Now what is two-phase method? Okay, so let's see here. The two-phase simplex method is an alternative method of solving an LPP in the algorithm, that is this solves LPP in two phases. Where in phase 1 we solve an auxiliary LPP to get either a feasible basis or conclude that the LPP has no solution. Okay, so phase 1 gives what? Phase 1 ensures that either the LPP has a feasible solution or there are no feasible solution. Okay, so then we go to phase 2. Okay, so this is a method you can solve the problems using the simplex method, BGAME method and the two-phase method. Okay, so in phase 2 we solve the LPP starting from the feasible basis found in phase 1. Okay, so this is the methods, that is what is phase 1, what is phase 2. Now here in phase 1 let the LPP be the problem of maximization problem. If we take the maximization problem, formulate the new problem by replacing the original objective function by the negative of the sum of the artificial variables. Okay, suppose there are x1, x2, x3 are three decision variables in the original problem, and we add suppose x3 and x4 are the slack variable, and slack variable, surplus variable, we can take any other variables 5 or 6. Okay, so suppose these three are the slack variables and this is a surplus variable, and for this surplus variable we have to take another variables which is suppose x7 is the here artificial variable. Okay, and one more thing, you note that the number of surplus variable is equal to the number of artificial variable. Okay, and you can say it oppositely, that is a number of surplus variable is equal to the number of number of artificial variable is equal to the number of surplus variable. Okay, so if there is there is only one artificial variable, therefore we just we write first for the phase 1 to the objective function as objective z, this is equal to 0 into x1 plus 0 into x2 plus dot 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 plus 0 into x6 minus x7. So this is known as the auxiliary objective function. Okay, so here auxiliary objective function, next replacing by called the auxiliary objective function. Okay, so this is the auxiliary objective function. Suppose be optimized by simplex method with the constraints of the original problem. So and if the problem has a feasible solution, the optimal value of the new objective function is 0. Okay, so this is the auxiliary objective function, and if the LPP has a solution, then the value of the objective function is 0. Okay, that is what? That is this x7, the value of the artificial variable also must 0. Okay, In that case, we have the feasible solution. That means what? That means this is the artificial variable can present in the basis or cannot be present in the basis. If these artificial variables are present in the basis, then the cost corresponding to this artificial variable must be 0. That is, the artificial variable present in the basis with a 0 cost. Okay, so this is the case. In that case, we get a solution, and otherwise we can't get the solution. Okay, so this is the thing, and then we proceed to phase 2. On the other hand, if the optimal value of the new objective function is non-zero, then the problem has no feasible solution. Okay, so that means what? That means if these artificial variables presents in the basis with a positive level, okay, then we can't get the solution. Okay, in that case, the problem has no feasible solution. Okay, so this is the case. And next, phase 2. So use the optimal solution of phase 1 as starting the solution of the original problem. Then the objective function is taken without the artificial variables and solve the problem by the simplex method. This is the simple simplex method. The first table of the phase 2 be almost identical with the last table of phase 1, differing only in the prices and the net evaluation. The optimal prices means what? Prices means the costs. Okay, so the net evaluation means Zj minus Cj term. The optimal solution thus obtained. If it exists, then the optimal basic feasible solution of the original LPP. Okay, so this is the phase 2. So this is the story behind the two-phase method. Now just I request you to read this just once, okay, and then take a problem. Now we comes to an problem, and before going to the problem, there is a tabular form to the procedure of the two-phase method. Okay, so number 1 is put the LPP in the standard form, that is add slack and surplus variables to the constant to put the LPP mean Z equal to C transpose X as that AX equal to B. Okay, this is I think max hoga. And second is add artificial variable, add a new variable to the left side of the constant if necessary, which is originally greater equal to or equal to type to get the unit basis matrix. Okay, so artificial variables, we already discussed that artificial variables comes only in the basis, that we adding the artificial variable to form the standard basis. Okay, next, change the objective function. So set up the new objective function equal to the negative of the sum of the artificial variables. So if there are two artificial variables, suppose x10 and x11, then we write what? We write the objective function as 0. All the coefficient of the other constants or other variables are 0. All the basic and non-basic variables are 0, and we just write minus x10 minus x11 as the auxiliary objective function. Okay, next, perform phase 1, that is set up the simplex table and use the iteration to reach the solution where all the net evaluation, that is the Zj minus Cj term greater or equal to 0, and this is the condition for optimality. And then check the feasibility, that is if the value of the objective function in step 4 is not 0, then the problem is infeasible. If that is, you think what happens here? Not 0 means what? The not 0 means this is the auxiliary function. That means these two artificial variables are present with a positive value in the basis. Okay, so to get the optimal, to get the feasible solution, these two artificial variables must be present or may not be present. If present, then presence with a 0 level. Okay, 0 level में ये बेसिस में रह सकता है, अदरवाइज ये कभी भी बेसिस में नहीं रहेगा. ठीक है, so in that case we got the solutions, would get the feasible solution. So remove the rest of the artificial variables, insert the old objective function, replace cost coefficient of the each variable, that is this is the original objective function now we take, and of the final table of phase 1 with the original cost coefficient of the objective function of the problem in the standard form. Therefore then we solve same way in the as we use in the simplex method. Okay, and perform phase 2, continue iterations until the optimal solution is reached or the problem becomes unbounded. So this is the table or tabular form, you can say. This is very helpful, I think, to operate all types of operation in phase 1 and phase 2. Okay, this is the shortcuts table, you can say. So let us take an example. So take maxima is z equal to 2x1 plus x2 minus x3, where 4x1 plus 6x2 minus plus x3 less equal to 8 less equal to 8 in greater equal to 8. Here you can see one thing, that here two types of inequality are mixed. Okay, so you can say this type of inequality, in these types of inequality you can solve by big M method also, and you can solve by using the two-phase method also. Okay, and I think there is some restriction in big M method, I think so. So if you know what is the restrictions of big M method to the what this method is two-phase method, then you can comment me. Okay, what is the, if there is any restriction, then you can comment me in the comment section. Okay, so solution: introducing slack variables x4 greater equal to 0, x4 x5 greater equal to 0. So these two are less equal to type constant, therefore here we need slack variables. This is a greater equal to type constant, here we need an surplus variable. Okay, and to form the basis we need an artificial variable which is x7 greater equal to 0. We write the LPP as in that standard form, this one, and these are the inequalities, and this is the here we get one surplus variable and one artificial variable. And note that here the standard basis formed by x4, x5 and x7, these three variables from the standard basis. See, the elements corresponding to this x4, that is the vector a4 is 1 0 0, the vector a5 is 0 1 0, and the vector corresponding to x7, that is a7 is 0 0. So these three form the basis. Therefore we take the initial basic feasible solutions, what, 0 0 0, x1 x2 x3 x4 x5 and x7. Okay, so corresponding to this, which the vectors which forms the basis. Okay, so x4 x5 and x7 form the basis, therefore we take the IBPS as this form. Okay, I think this is clear. Now the auxiliary objective form, we form this auxiliary objective function, that is, this is, in this case the only variable is present with a negative sign, that is, which is the artificial variable. Okay, so this is the auxiliary function, auxiliary objective function. Okay, now starting the table, this CBBXB, the forms the basis, forms x4 x5 and x7 form the basis, and their corresponding basis vectors are a4 a5 a7, and we write here the cost corresponding to x4 x5 and x7, 0 0 and -1, and b means 8 1 4, we all know that, and this is the coefficients of this above constants. Okay, so this is the simple table you can calculate by using your known calculation, which we already said. Okay, so here we see that now we have to calculate what is entering vector and what is outgoing vector. Okay, so here zj minus cj are not all greater or equal to 0. That means this is optimality condition is not satisfied, therefore we go to the next iteration, and here see the negative most number, that is this is -3, that is z2 minus c2 is the incoming vector, that is a2 is the incoming vector. Okay, so here it is right that a2 is the enters in the basis. Okay, and then what, then we calculate the mean ratio corresponding to this vector. Okay, so 8 by 6, this is equal to 4 by 3, this is negative, therefore we avoid this, and this is 4 by 2, this is 4 by 3, so 4 by 3. And here one thing is, note that 4 by 3 and 4 by 3 are same. Okay, so you can take any one of them as the departing vector from the basis. Okay, so here in this case I think a4 is chosen as a departing vector. Okay, you can take the a7 also for the departing vector, since these mean ratio are to same mean ratio. Okay, there is no problem. So see here so here in this book there is taken there is a2 is enters the basis and a4 departing vector of the basis, and this is 6 is the key element. Okay, so there is no confusion. I think if there is any confusion, then you can comment me. Now we calculate the remaining table by using the calculations we just said, and you can see here also the first iteration. Okay, this is the operation you can use from the first table to the next table. Okay, so this is the calculation. I also said the shortcut trick for the calculations. Okay, so you can check the previous videos for the shortcut trick. Okay, so we now get the table as this one. So now we see that here A2 enters the basis and A4 leaves the basis. Okay, so A2, A5 and A7 is now forms the unit vector. So this vector and this vector forms the basis vector. Okay, so now after all the calculations we get Zj minus Cj, this is equal to all are greater or equal to 0. That means optimality conditions is satisfied. Okay, so if the optimality condition is satisfied, that is key. What? Phase 1 ensures the existence of the feasible solutions of the LPP. Okay, so Zj minus Cj greater or equal to 0, so the optimal basic feasible solution of the auxiliary LPP has been attained. Also max Z star equal to 0, this is the condition we already discussed above in the summary of the two-phase method. And the artificial basis vector A7 presence in the basis at 0 level. Okay, so we proceed phase 2. So this ensures that the LPP has an feasible solution. So we proceed phase 2. If the conditions other conditions happen, that means if the artificial vectors presence in the basis, here x7 is the artificial vector presence, a7 is the artificial vector presence in the basis with a positive level. Suppose this term instead of 0, this terms is any positive number. Okay, suppose this is 1, then what happening? That means what? That means the artificial vector presence in the basis with a positive level. Okay, this said with a positive level. If that happens, then we stop the problems here and say that the problem has no feasible solutions. Okay, so phase 1 ensures the existence of the feasible solutions of the LPP. Clear? I think. Now we proceed LPP. We proceed phase 2. Okay, so new objective function is the now comes the with the original objective functions. Okay, so this is the original objective function, and now we calculate the simplex table. The similar case, the constant are same from the from this two-phase method. Okay, we take the constant from this table. Okay, so these are the constant, and just here only change is what? Only change is the objective function in the objective function. Okay, so this is the case. So here now from this table we see that here A2 and A4. So in this case, after calculating the first table, see that minus here 1 minus minus 4 by 3 is present, and only this is only the minus term. Therefore this A1 enters the basis, and if we calculate the mean ratio, then what? 4 by 3 by 2 by 3 and 9 by 7, and minimum of these two numbers is this one, that is A5 leaves the basis, and intersection of these two elements is 7, that is 7 is the key element. Okay, so 7 is the key element, A5 is the what? A5 is leaves the basis and A1 enters the basis. Okay, so this is happen after a table, starting table of phase 2. Okay, now we apply the same case, the same situation, row operation. Okay, and you can apply also the shortcut tricks. Okay, which I already discussed. So this is equal to, we see here A2, A1 and A7. Okay, so see, after calculating all the necessary calculations, you see that what? All Zj minus Cj greater or equal to 0. Okay, that is optimality condition satisfied. And here see that A7 is present in the basis with a 0 level, that is here the optimality condition is satisfied. Okay, so the optimal solution is what? X2 equal to 10 by 21, x1 equal to 9 by 7, x3 equal to 0, and remaining all the other variables are 0. Okay, so x1 is 9 by 7, 10 by 21, x3 equal to 0. These are the original decision variables which are given in the questions. Okay, so and the maximum value of z, we put just the values of x1, x2, x3 in the objective function, which has to be maximized. Okay, so this is the answer, 64 by 21. I think you understand this question. And this question here, one note is that since the optimal table in the net evaluation of the non-basic vector A6 is 0, so the given LPP has an alternative solution. Okay, so this is an interesting problem I take here. See here A6, which is a non-basic variable, A1, A2, A3 are the basic vectors, A4, A5, A6 are the non-basic vectors. Okay, and A7 also non-basic vector. Here see that this forms the basis, therefore the Zj minus Cj term corresponding to these three are 0. There is no problem. Now this is basic vectors, but zj minus cj presents with a positive label, and these two are the non-basic vectors. These three are the non-basic vectors, but in between these three vectors, what there is another non-basic, there is one non-basic vector which is present with a zero level, that is the net evaluation is 0, and this is the concept of alternative optimal solution, which we already discussed. Okay, so this is a very interesting problem, you can say, and this is the session for today's class. So how was the session? If the session is helpful for you, then please give a like to this video, share with your friends, and subscribe the channel. Okay, thank you. See you again in the next video.